All right, in this video, we're going to introduce what are called parallel pipeds in R3, formed by three vectors, A, B, and C. Okay, so this is really similar to what we do when we form the parallelogram formed by two vectors. Here, though, we're going to look at the parallelograms formed by the pairs A and B, then A and C, and then B and C. Okay, and then doing that and translating things around, we get this distorted three-dimensional box. Okay, so we would like to compute the volume of this box, and so to do that, well, that's going to be the area of the base of the box times the height of the box. So what's the area of the base? Well, if I choose the base to be this parallelogram formed by A and B, we know that the area of that parallelogram is the magnitude of the cross product of A and B. So that's the area of the base. How about the height? Well, notice that if I take the cross product of the vectors A and B, that's going to give me this vector here. You see in orange. Right? It's following the right-hand rule. It's pointing upwards. And so the height of the box, right, well, that's just equal to the magnitude of the projection of this blue vector C onto this orange cross product vector. Okay, so that's the height of the box. Now, as long as the angle between C and the cross product vector is acute, like you see here in this figure, okay, the height then will be the scalar projection of C onto the cross product vector. Remember, the scalar projection, generally speaking, is the sine magnitude of the projection. So as long as that angle is acute, this height will be that scalar projection. Now, remember, the definition of the scalar projection, right, that was equal to the dot product of the two vectors, so C dotted with this cross product. And then we divide by the magnitude of the vector we're projecting onto, which in this case is A cross B. And now, noting that the magnitude of A cross B drops out, this is equal to C dot this cross product of A and B. Okay, but again, that will hold provided the angle between C and this cross product vector is an acute angle. If that's not the case, what will we be looking at? Well, if it's not the case, that means that this cross product vector will be pointing downwards. So for example, let's say B was actually the green vector and A was the red vector. Then the cross product vector following the right-hand rule would point downwards. But see, the box is going to have, it's just going to be oriented differently, but the box is going to have the same volume. Okay, so for more general angles, okay, we just take the absolute value here of whatever this number comes out to be, just to account for that that sign difference coming from how we measure the scalar projection. Okay, cool. Now the last thing I want to say is that for this particular diagram, I chose the base of the box to be the parallelogram formed by A and B, but I just as well could consider the base of the box to be this parallelogram formed by B and C, or this parallelogram formed by A and C, right? So for that matter, right? So if I, in other words, permute the vectors around, right, all of these products are going to give me the same volume. Okay, so to summarize all that, the following result: the volume of the parallel piped formed by the vectors A, B, and C is as follows. And notice here I'm being careful to distinguish between these vertical bars when they're an absolute value and when they're a determinant. Okay, so on this first expression, A dot this cross product to B and C, this being a dot product is a scalar quantity, right? It's just a real number. Maybe it's 10 or negative 15. I'm taking the absolute value of this number here. But now once we get to this part, okay, well, if you write this out in terms of components, it turns out that this dot product of this cross product, it turns out to be expressible in terms of just this single determinant. And so we just get the determinant of this 3 by 3 matrix, and then we're taking the absolute value. And this, by the way, A dot B cross C, this is known as what's known as a scalar triple product. Okay, so now let's go ahead and do an example. Finish things out, make a little space here. So looking at number 9, It says find the volume of the parallel pipette with adjacent sides PQ, PR, and PS. And then you're given the coordinates of P, Q, R, and S. That's there. So I'm going to first form the vectors PQ, PR, and PS. Those are going to be the A, B, and C, right, for my distorted box. And so then, to find the volume of the parallel pipette formed by these three vectors, well, all I do is look at the absolute value of this scalar triple product. So PQ dot PR cross PS, which, as we just noted in the last slide, that can be computable in terms of this 3x3 determinant. Just lay out the components of PQ, then the components of PR, then the components of PS. If you crank through this determinant, you wind up getting 16, and the absolute value of 16 is, well, 16. So that is the volume of our parallel pipette, and that does it for this video. Thanks so much.